Detroit didn't lose the early 1960s street wars because it lacked horsepower. It lost because it misunderstood physics. While Ford and Chevrolet doubled down on bigger engines and louder promises, a small group of Chrysler engineers quietly rewrote the rulebook. Their weapon wasn't a V8, a supercharger, or exotic fuel. It was an intake manifold that looked wrong, sounded wrong, and broke every assumption about how power should be made. The result was deeply uncomfortable for the establishment. Humble Plymouth Valiants, embarrassing Mustangs, and Chevys in real-world driving. This wasn't rebellion through brute force. It was destruction through engineering precision. The accidental racing engine. Picture this. It is late 1959. The American highway is dominated by chrome-laden giants, vehicles defined by massive tail fins and strictly ornamental sheet metal. But inside the executive boardrooms of Detroit, the mood is not one of triumph, but of panic. The consumer tide is turning violently. Americans are beginning to ignore the domestic behemoths in favor of smaller, more efficient European imports, like the Volkswagen Beetle. The Big Three know they have to pivot, and they have to do it immediately. This panic births the compact class of 1960. General Motors responds with the Chevrolet Corvair, a radical departure using an air-cooled flat-six engine mounted in the rear. Ford plays it safe with the Falcon, utilizing a strictly conventional vertical inline six that is essentially a scaled-down version of their existing technology to minimize risk. Then, there is Plymouth. While their competitors look to the past or to radical experiments, Chrysler engineers led by Willem Weertman start with a clean sheet of paper. They create the Valiant, and under its hood sits an engineering marvel that will outlive them all. The G engine, universally known as the Slant 6. The first thing you notice when opening the hood of a 1960 Valiant is that the engine looks broken. The entire block is leaning over. This is the defining characteristic of the Slant 6 architecture, a 30-degree inclination toward the passenger side. This was not a stylistic flourish, but a solution to a complex packaging problem. By tilting the block, engineers achieved a significantly lower overall engine height. This allowed stylists to design a low, sloping hood line that mimicked the aerodynamic European aesthetic buyers were craving. But the benefits went far beyond styling. The tilt created a natural pocket of space on the side of the block for the water pump. By offsetting the pump, rather than mounting it on the front, Chrysler shortened the engine's total length by 4 inches compared to a standard straight 6. This compact footprint meant the engine could fit into tight engine bays originally designed for much smaller power plants. Where the Slant 6 truly separates itself from the Falcon and Corvair is in its structural integrity. This was supposed to be an economy engine for getting groceries, but it was built with the robustness of heavy industrial machinery. The block utilizes a deep skirt design, meaning the heavy cast iron extends well below the center line of the crankshaft. Most engines of the era ended the casting right at the crank, but the Slant 6 enclosed it completely. This massive casting creates a rigid structure that resists twisting and distortion under high loads, minimizing the vibration that typically plagued small displacement engines. To support the rotating assembly, engineers selected a 4-main bearing setup. While a lower bearing count usually suggests an economy focus, the physical dimensions of these bearings tell a different story. They are massive. The main bearings in this modest 6-cylinder engine share the exact same dimensions as those found in the legendary 426 Hemi V8. This provides the crankshaft with a level of support capable of withstanding the torsional stresses of extreme racing environments, far exceeding the requirements of a daily commuter. The result was a strange engineering paradox. Ford and Chevrolet had successfully built adequate economy cars for the masses. Chrysler, in their pursuit of durability and packaging efficiency, had accidentally engineered a competition-ready block disguised as a thrift store motor. The monster in Cell 13. The metamorphosis of the Plymouth Valiant from a polite economy car into a pavement-eating predator did not happen in a marketing meeting. It happened behind the heavy, soundproof doors of Chrysler's Dyno Cell 13. This was the domain of Pete McNichol and Tom Hoover, engineers who operated with the spirit of hot rodders rather than corporate employees. Hoover, who would later become a godfather of the legendary Ram Chargers racing team, understood that to dominate the upcoming NASCAR Compact Series, standard engineering practices had to be abandoned. They needed to homologate a package that would satisfy the rulebook, while completely circumventing the spirit of an economy class. The result was engineering code 785, a high-performance suite known to the world as the Hyper Pack. The visual centerpiece of this transformation was the intake manifold. In an era where most six-cylinder engines gasped for air through restrictive, short log manifolds that starved the outer cylinders, the Hyper Pack looked like an alien organism had latched onto the engine block. It featured 6 individual, incredibly long aluminum runners that snaked across the engine bay in a tangled formation that enthusiasts immediately dubbed the Bunch of Bananas. But this chaotic appearance was actually a masterclass in acoustic physics. McNichol and Hoover were weaponizing a concept known as Helmholtz resonance. In a standard engine, air flows in, mixes with gas, and burns. In the Hyper Pack, the air is treated as a heavy moving column with mass and inertia. When the intake valve slams shut, the high-velocity air rushing down that long runner crashes against the back of the valve. It has nowhere to go, creating a high-pressure pulse, essentially a traffic jam of air molecules. This pressure wave bounces off the valve and travels back up the runner to the plenum, then reflects back down toward the cylinder. The engineers calculated the runner lengths, specifically tuning them between 15 and 20 inches, so that this reflected high-pressure wave would arrive back at the intake valve exactly as it opened for the next cycle. This effect, known as inertial charging, rammed air into the cylinder with a force that mimicked a supercharger, creating a naturally aspirated boost of up to 3 psi. To feed these hungry runners, the team mounted a massive Carter AFB 4-barrel carburetor, more than 12 inches away from the cylinder head ports. This distance was critical to maintaining the velocity of the air charge, but airflow means nothing without the mechanical hardware to process it. Deep inside the block, the team installed a camshaft that had no business being in a streetcar. It was a Racer Brown ST21 grind, featuring a radical 0.520-inch lift and 286 degrees of duration. To put that in perspective, a standard camshaft is designed for a smooth idle and low-speed manners. The ST21 was designed to hold the valves open as wide and as long as possible, creating a rough, lumpy idle that signaled aggressive intent. The supporting cast included high-compression domed pistons to squeeze the mixture and split cast-iron headers that separated the exhaust pulses into 2 groups of 3, merging into a large 2.5-inch exhaust system. The numbers generated in Cell 13 were staggering. The base 170 cubic inch engine produced a respectable 101 horsepower. With the Hyper Pack, that number spiked to a verified 148 horsepower. This wasn't just a bump, it was a 46% increase in output. More impressively, the engine was now producing 0.87 horsepower per cubic inch. This specific output didn't just beat the Falcon and the Corvair, it rivaled the efficiency of the highest performance V8s of the era. A televised execution at Daytona. In January 1960, NASCAR founder Bill France launched a grand experiment at Daytona International Speedway. He called it the Cannonball Compact Division, a new racing class designed specifically to showcase the emerging wave of American small sedans. With CBS television cameras rolling and legendary newsman Walter Cronkite in the booth, the event was intended to be a friendly, promotional exhibition that would introduce the American public to the virtues of the compact car. France expected close racing and a celebration of fuel economy. Instead, he presided over a televised massacre. The starting grid featured a who's who of racing royalty, including Lee Petty, Richard Petty, Joe Weatherly, and Fireball Roberts. On paper, it looked like a competitive field. In reality, the race was decided before the engines even fired. Ford and General Motors had fundamentally misunderstood the assignment. They treated the event as a marketing demonstration, bringing Ford Falcons and Chevrolet Corvairs that were essentially bone stock. Some of these cars still bore their original dealership window stickers, prepared with nothing more than safety belts and a number painted on the door. Chrysler, conversely, did not see this as a parade. They saw it as combat. They arrived at Daytona with a fleet of 7 Plymouth Valiants, every single one equipped with the A785 Hyper Pack. The first heat took place on the 3.81-mile road course, run in a clockwise direction that reversed the standard flow of the track. As soon as the green flag dropped, the disparity became comically evident. The stock Falcons, with their 90 horsepower engines and restrictive intake logs, wheezed their way out of the corners. The Corvairs, battling the inherent oversteer of their rear-engine layout, struggled to find traction. The Hyperpack Valiants simply disappeared. The physics of the long-runner intake meant that every time a Plymouth driver touched the throttle at the apex of a turn, the engine responded with a surge of torque that the competition could not replicate. The result of the road course heat was absolute. Marvin Ponch crossed the finish line first in his Valiant. He was followed by Larry Frank in a Valiant, then Jeff Stevens in a Valiant. The pattern continued relentlessly until Plymouths occupied the first 7 positions on the leaderboard. The highest finishing non-Chrysler entry was Joe Weatherly in a Ford Falcon, who finished in 8th place, nearly an entire lap behind the leaders. But the true display of horsepower was reserved for the second heat. 20 laps on the high-banked tri-oval. This was a test of sustained high-speed endurance, and the Valiant faced a significant aerodynamic disadvantage. The car was a sedan with the aerodynamic profile of a brick. However, the Hyperpack's ability to force-feed air into the combustion chamber overcame the wind resistance through sheer brute force. While the competition hit an aerodynamic wall, struggling to push past 90 miles per hour, the Valiants kept pulling. Marvin Ponch, piloting the lead Plymouth, did not just win. He set a blistering pace that shocked the paddock. He averaged 122.282 miles per hour over the course of the heat. This was a speed that the 90-horsepower Falcons and 80-horsepower Corvairs could never mathematically achieve, regardless of how well they were driven. The Valiants once again swept the podium, taking first, second, and third. For the 17 million viewers watching at home, the message was unambiguous. This was not a competition between equals. It was a public execution of Ford and General Motors' engineering departments. The power-to-weight paradox. The claim that a 170 cubic inch 6-cylinder engine could embarrass the V8 muscle cars of the 1960s sounds like heresy. In the traditional American automotive catechism, displacement is king, and there is no replacement for cubic inches. But the dominance of the Hyperpack Valiant was not based on raw displacement. It was based on a ruthless adherence to the physics of power-to-weight ratios. When you strip away the marketing and look strictly at the math, the reason for the Slant 6's superiority becomes undeniable. The 1960 Plymouth Valiant was already an anomaly in Detroit. It utilized unibody construction and incorporated approximately 60 pounds of aluminum in the chassis and engine components, making it exceptionally light. When equipped with the Hyperpack, the car weighed just over 2,000 pounds and produced 148 horsepower. If you run the numbers, that results in a power-to-weight ratio of 13.9 pounds per horsepower. To understand how aggressive that figure is, you have to look at its competition. The Ford Falcon dragged 25 pounds for every single horsepower it produced. The Chevrolet Corvair was even worse, at 28 pounds. The Hyperpack wasn't just faster than its direct rivals, it was nearly twice as responsive. This mathematical advantage held true, even when compared to the performance icons that arrived years later. When the Ford Mustang debuted in 1964, the base 6-cylinder model carried a power-to-weight ratio of 25:1, making it nearly half as efficient as the 1960 Valiant. Even when the Mustang was equipped with the legendary 289 V8, the advantage was not as clear-cut as history remembers. The installation of a cast-iron V8 added nearly 340 pounds to the nose of the car. While the V8 had more peak horsepower, that extra mass dulled the car's reflexes. In tight cornering or technical driving, the lightweight, punchy Valiant could change direction and accelerate out of turns, while the nose-heavy V8 was still fighting its own inertia. But the real secret to the Hyperpack's street reputation lay in the first 60 feet. This is the distance that determines the winner of a stoplight drag race, and it is governed entirely by low-end torque, not high-end horsepower. This is where the long-runner intake manifold proved its genius. V8 engines of the era typically suffered from lazy, low-end response. Their large combustion chambers and heavy reciprocating assemblies required time to build momentum. They were powerful, but they were slow to wake up. The Hyperpack was the opposite. Because those long intake runners were acoustically tuned to the 3,000 to 4,000 revolutions per minute range, the engine produced a massive localized spike in torque, right where a driver needs it most. When the light turned green, the Hyperpack didn't need to wind up. The inertial supercharging effect provided an instant, violent shove. In amateur drag racing, hyperpack-equipped cars consistently humiliated V8 Mustangs and Chevys in the first 60 feet of the track. The Valiant would leap forward, putting 2 or 3 car lengths on the competition before the V8 could even reach its power band. By the time the V8 began to breathe and utilize its displacement advantage at speeds over 100 miles per hour, the race was usually over. For the reality of street driving, the Hyperpack was simply the superior engineering solution. The price of absolute victory. In the world of professional motorsport, winning is usually the primary objective. But there is a strange paradox in racing. If you win too much, you become a liability. The absolute dominance of the Hyperpack Valiant in 1960 did not secure its future. It signed its death warrant. NASCAR founder Bill France was in the business of selling tickets and television contracts, and those business models rely on drama, conflict, and close finishes. A single manufacturer sweeping the top 7 positions is not a race, it is a parade, and parades do not generate strong ratings. The backlash was immediate. The playing field was not level, and rather than forcing Ford and General Motors to engineer better cars, the regulatory bodies simply changed the rules to penalize the winner. In 1961, NASCAR altered the format of the compact division. They eliminated the high-banked oval heat entirely. This was a calculated move designed to neutralize the Valiant's primary advantage, its ability to sustain high speeds that the unaerodynamic Falcons and Corvairs could not reach. The series was restricted to a single road course event, hoping that the lower speeds would equalize the field. It didn't work. Hall of Famer Lee Petty wrestled a Hyperpack Valiant around the twisty infield course to win the 1961 race anyway, proving that the engine was superior regardless of the track layout. Faced with the reality that they could not win against the Chrysler engineers, Ford and General Motors effectively took their ball and went home. They were unwilling to invest millions of dollars into a racing class where they were destined to be the villain in a Plymouth success story. Under pressure from the big manufacturers to protect their brand prestige, NASCAR quietly allowed the Cannonball Compact division to fade into obscurity. By late 1961, the division was discontinued. The Hyperpack had been too successful for its own good. But the death of the program wasn't just political, it was financial. On the dealership floor, the Hyperpack faced a brutal economic reality check. The kit carried a price tag of $403.30. In 1960, the base price of a Plymouth Valiant was roughly $2,000. This meant the performance package cost nearly 25% of the vehicle's total value. Adjusted for inflation, that is the equivalent of spending over $4,000 today, just to upgrade the intake and exhaust on an economy car. It was a massive expenditure that very few buyers could justify. Furthermore, the driving experience was far from civilized. Corporate memos from the era explicitly warned sales staff not to market the Hyperpack to Mr. Average Motorist. The radical camshaft profile that won races caused a rough, shaking idle that terrified normal commuters. The intake manifold lacked a heat riser, meaning that in cold climates, the fuel would drop out of suspension, making the car nearly impossible to drive until the engine block was fully heat-soaked. It was a race car part trying to live in a commuter world. Simultaneously, the heartbeat of Chrysler Corporation was shifting. By 1962, the engineering focus had pivoted violently toward the burgeoning muscle car wars. The factory began pouring its resource into the 413 Max Wedge and preparing for the return of the 426 Hemi. The specialized high-revving Slant 6 simply got lost in the noise of 8-barrel carburetors and massive displacement V8s. By 1963, thousands of dollars worth of unsold Hyperpack inventory sat collecting dust on dealership shelves. As parts managers needed to clear space for the new small block 273 and 318 V8 components, these exotic 6-cylinder parts were deemed obsolete. Many of them were sold for pennies on the dollar, or, more tragically, simply thrown into the dumpster behind the service bay. The holy grail of Mopar. There is a profound irony in the life cycle of the Hyperpack. The very components that dealership mechanics were throwing into trash bins in 1963 have transformed into some of the most sought-after artifacts in the automotive world. Because so few kits were sold, and even fewer survived the decades of neglect, the original A785 intake manifold has become unobtainium. For the dedicated subculture of enthusiasts known as Slant Sixers, finding one of these manifolds is not just a purchase, it is an archaeological discovery. The market reflects this scarcity. In the current collecting landscape, a genuine original 1960 cast aluminum hyperpack intake manifold, even in used condition, typically commands a price between $1,000 and $1,200. If a collector is lucky enough to find a confirmed new old stock kit, complete with the original hardware and that massive Carter carburetor, they have found a unicorn. These complete packages rarely change hands publicly, but when they do, prices easily exceed $1,500. But for those who cannot find an original, the path is fraught with manufacturing drama. The reproduction market is divided by a stark gap in quality. In the 1990s, legendary Slant 6 engineer Doug Dutra produced a limited run of intakes using original Chrysler patterns. These Dutra Hyper packs are revered for their precision and are almost as valuable as the originals. Conversely, later reproductions from other aftermarket suppliers like Clifford Performance have faced criticism from the community. Builders often report scabs, bubbles, and cavities in the aluminum casting, evidence of inferior scrap metal being used in the foundry process. The DNA of modern horsepower. The strange snaking aluminum runners of the Hyperpack eventually disappeared from dealership shelves, leading many to believe the technology was a failure. But in reality, the Hyperpack was not a dead end. It was a rough draft. The engineering principles that Pete McNichol and Tom Hoover established in 1960 did not vanish. They went dormant, waiting for technology to catch up. Today, the physics of pressure wave tuning that powered the Valiant are ubiquitous in global automotive design, living on under the name Variable Length Intake Manifold, or VLIM. The primary limitation of the original Hyperpack was that it was static. Its runner length was fixed in aluminum. It was a brilliant solution for a specific problem, providing a massive torque boost at 4,000 revolutions per minute, but it became a restriction at higher speeds. Once the engine pushed past 5,500 revolutions per minute, those long runners that helped create torque became a bottleneck, choking off airflow. It was a one-trick pony. Modern engineering has solved this problem through variable geometry. Contemporary engines, such as those found in BMWs, or the screaming 5.2-liter Voodoo V8 in the Ford Mustang GT 350, utilize the exact same acoustic physics as the Valiant, but they add a mechanical brain. Inside the intake plenum of these modern beasts sits a series of electronically controlled butterfly valves. At low and mid-range engine speeds, these valves remain closed, forcing the air to travel through a long, narrow path. This capitalizes on low-speed sonic pulses and high air velocity to generate torque, effectively mimicking the bunch of bananas design of the Hyperpack. However, as the driver stays on the throttle and the RPM climbs, the computer commands those valves to snap open. This instantly creates a shortcut for the air, bypassing the long runners in favor of a direct, wide-bore port. The engine transforms in milliseconds, switching from a torque-heavy street motor into a high RPM race engine that can breathe without friction. The modern driver gets the best of both worlds, the low-end jump of a 1960 Valiant and the top-end scream of a modern supercar. The methods of designing these systems have also evolved. In the days of DynoCell 13, McNichol and his team relied on physical prototypes, spending hundreds of hours cutting, welding, and telescoping metal pipes to find the perfect length. Today, that physical labor has been replaced by computational fluid dynamics. Engineers use advanced 1D and 3D simulation software like Ricardo Wave to visualize pressure waves before a single part is cast. They can tune the manifold resonance across the entire power curve with mathematical precision. Every time a modern engine surges with torque, utilizing a column of air to force-feed a cylinder, it is channeling the spirit of the Hyperpack. The saga of the Plymouth Valiant Hyperpack is more than a racing footnote. It is the ultimate proof that comprehensive systems engineering can dismantle raw displacement. Chrysler proved that an economy inline-six, fortified by a deep skirt block and advanced induction physics, could out-accelerate the most prestigious engines of its time. This durability was not an accident. The Leaning Tower of Power earned its reputation for being indestructible because it was overbuilt, using forged steel internals and massive bearings designed to survive the high banks of Daytona at 122 miles per hour. It stands as a testament to the fact that the most innovative solutions often reside in the least expected places.